So far, I have told you about sharing the public key through valid digital certificates. Digital signatures add another layer of authenticity and non-repudiation. Digital signatures follow a different approach for identity verification, wherein the individuals use their private key to create digital signatures, which then can be decrypted using the public key from its key pair to verify the authenticity of the signature. Digital Signature Algorithm, DSA, Rivet-Shamir-Adleman Signature Algorithm, RSA, and Elliptic Curve Digital Signature Algorithm, EXA, are the few commonly recommended secure algorithms for creating digital signatures. Hello, welcome to the next episode of Get Certified Together program by TechnoCoff, your free online knowledge sharing community. Visit our website, www.technocoff.com for more information. In this episode, we will be covering the next section of the CompTIA Security Plus certification exam. Let me start with the very first topic, cryptography. Cryptography is the mechanism of encrypting and decrypting any information using computational algorithms to ensure the protection of data in transit or data at rest. Cryptography ensures following. Number 1, confidentiality of data in all three states, at rest, in transit, and in use. This can be achieved by using encryption. Number 2, the integrity of data. This can be achieved by using hashing. Number 3, authentication of the users accessing a system. This can be achieved by using key pair. Number 4, data obfuscation, or converting data unintelligible and unclear. This can be achieved by using salting. Number 5, non-repudiation. This can be achieved by using digital signatures. And number 6, transport layer security, TLS. This can be achieved by using digital certificates. There are broadly two types of cryptography mechanisms for encryption and decryption. Symmetric encryption uses the concept of a single key for encrypting and decrypting the data. Asymmetric encryption uses the concept of key pair, with one public and one private key, for encrypting and decrypting the data. Data encrypted with the public key can be decrypted using the private key from the same pair. And data encrypted with the private key can be decrypted using the public key from the same pair. Let us understand more about these two types of encryption mechanisms and different commonly used algorithms. Symmetric encryption is the single key encrypt and decrypt mechanism. Various algorithms can be used for this kind of encryption. DES, or DES, stands for Data Encryption Standard, uses 64-bit blocks and 56-bit key lengths to encrypt the data. 3DES, or 3DES, performs DES functions 3 times over, hence called 3DES. It uses 64-bit blocks and 112-bit key lengths to encrypt the data. AES, or Advanced Encryption Standard, uses 128-bit blocks and uses 3 different key lengths: 128-bit key, 192-bit key, and 256-bit key. Do note that the higher the length of a key, the more secure will be the encryption, but with a trade-off in computational time. DES itself is considered insecure and not used in production these days. Another symmetric encryption algorithm is 2FISH, which uses 128-bit blocks and 3 different key lengths: 128-bit key, 192-bit key, and 256-bit key. Using the same key for encrypting and decrypting may sound simple, but simple things are not always secure. Hence, asymmetric encryption uses the key pair, with one public key and one private key, to encrypt and decrypt any data. In the asymmetric encryption mechanism, user A wants to send confidential data to user B. First, user A will use user B's public key to encrypt a message. User B holds the private key from pair, and therefore can decrypt this confidential data. The key thing to remember here is, private key always stays with the user who generated the key pair, while the public key can be shared with anyone. RSA, or Rivet, Shamir, and Adleman, is the most commonly used algorithm for asymmetric encryption. It uses 1024 to 2096-bit key length. PGP, or Pretty Good Privacy, combines symmetric and asymmetric encryption for additional security. In PGP, data is encrypted with a single key, generated using the symmetric encryption mechanism. This key is then shared with end users by encrypting it with the public key of the key pair generated using asymmetric encryption. So, the recipient has to first decrypt the message using its private key to extract the symmetric key. This symmetric key shall be then used to decrypt the actual data. So far, in the discussion we had, the most important aspect of the whole encryption mechanism is the key. The key must be secure and authentic. For any encryption to be successful and reliable, the confidentiality of a key is the single most important factor, which, if compromised, can lead to repercussions. Some of the ways to ensure the secure exchange of a secret key are Diffie-Hellman, key escrow, key stretching, and hardware security modules. Diffie-Hellman key exchange is a method of securely exchanging cryptographic keys over a public channel. Key stretching is the mechanism to add random salt values to a key for increasing its length. Key escrow uses an escrow arrangement where a third party holds all the keys safely and provides them to the user in case the original is lost or compromised. When discussing asymmetric encryption, I mentioned that a public key is shared openly for the sender to encrypt the data and send it to the receiver, who owns the private key from the key pair, but who validates whether the public key has been used to encrypt the message in the first place, is indeed part of the receiver's key pair. Public key infrastructure, or PKI, is the mechanism of trusting the source of any public key by issuing the X.509 digital certificates. These certificates are associated with the individual's or organization's identity. They are approved by the certificate authorities, or CA. Any user who wants to create a digital certificate for its public key needs to send a valid certificate signing request, CSR, to certificate authorities, which verifies all details of the individual and issues certificate. This certificate has many use cases. It can be used to identify servers and websites in the client browser's TLS session. They can also be used to encrypt messages, using the public key associated with them. Certificate chaining is the scenario where a digital certificate is validated by a chain of CS, both internal and external, to the organization. The topmost authority in the certificate chaining scenario is called root CA. We can also have the same certificate for the multiple domain names. This common certificate is called the wildcard certificate. Commonly used certificate formats are .pem, .der, .crt, etc. Hashing is the mechanism to turn readable information into a random set of data. This random data, once reverted, gives us actual information back. Any change in input, no matter how much small it is, will completely change hashed output value. The few commonly used hashing functions are Message Digest 5, or MD5, which uses 128-bit hashes. MD5 is proven insecure now. More advanced, Secure Hash Algorithm, or SHA, is used now. SHA-1, with 160-bit hashes, SHA-2, with 224, 256, 384, and 512 bits hashes, and SHA-3, with dynamic bit length, are three different commonly used SHA hashing algorithm variants. So far, I have told you about sharing the public key through valid digital certificates. Digital signatures add another layer of authenticity and non-repudiation. Digital signatures follow a different approach for identity verification, wherein the individuals use their private key to create digital signatures, which then can be decrypted using the public key from its key pair to verify the authenticity of the signature. Digital signature algorithm, DSA, Rivet-Shamir-Adelman signature algorithm, RSA, and elliptic curve digital signature algorithm, ICSA, are the few commonly recommended secure algorithms for creating digital signatures. TLS Handshake is a subcategory of PKI-based communication using digital certificates for secure communication between server and client, used by the HTTPS protocol. For this handshake, the web server sends its public key with the digital certificate to the client's web browser, which then verifies all information for the web server, with mentioned CA in the certificate. Once it's verified, the public key sent with this digital certificate is used by the client to encrypt an ephemeral session key. This encrypted session key is sent to the server, which decrypts the message, using its own private key. All communication from now onwards uses this ephemeral session key, which is temporary and unique, hence cannot be read by the eavesdropper. This brings us to end of the episode 4 of the Get Certified Together podcast from Technicoff on the CompTIA Security Plus exam. In episode 5, I will proceed to the next section of the exam, Cloud Security. Thanks for listening.